Let's see the example on calculation of power requirements. So for this question, a fermentation broth of viscosity 10 power of negative 2 Pascal second with a density of 1000 kg per meter cube is agitated in the 50 meter cube buffer tank by using the marine propeller with a dimension of 1.3 meter in diameter. The tank geometry is specified in figure 6.13, and what you need to do is to calculate the power required for a stirrer speed or tip speed or the agitation speed of 4 per second. First, you need to calculate the Reynolds number using the equation of Reynolds. Then, from the Reynolds number, find the power number, okay, based on the lines for the type of propeller used. Okay, so we see here the Reynolds number falls under the turbulent region. Okay, for number 3, marine propeller, and the power number on your left side is equals to 0.35. From the plot, okay, the power number is 0.35. Therefore, by using the equation P equals to N P rho and I cube di power of 5, then find the power requirement for the question. Then this is the answer for the power requirement for the fermentation. This figure shows the Reynolds number and the power number, okay, for various impellers. Alright, so we have different types of impeller with blades, and this is the dimension for the impeller, width over D of the impeller. Okay, you can use this for design also. And then based on the type of impeller, if you calculate the Reynolds number, then you will find at which region it falls and also the power number. Power requirement for ungassed non-Newtonian fluids. So it's difficult to estimate the requirement because of the variation in terms of the viscosity mu, as the mu changes with the shear rate. The non-Newtonian fluid is highly viscous, hence it's very difficult to achieve turbulent flow. So the power number is not constant. From the apparent viscosity for power loss fluid, okay, using the equations here, then you have that the Reynolds number is equals to the equation shows here. Okay, because we know that the non-Newtonian fluid is very viscous. So in the fermentation or the production of a non-Newtonian fluid product, so as time increase, the viscosity of the fluid will increase. Figure here shows the correlation between the power number and Reynolds number for a Rushton turbine in aerated fluids. So the lines here, we have lines of Newtonian fluid and non-Newtonian fluid. Similar, if we have different fluid, okay, then what you have to do is similar to the previous example shows, you have to calculate the Reynolds number. So based on the Reynolds number, find the region and then refer to the type of fluid lines here, which one, Newtonian or non-Newtonian, and then you find the power number for the fermentation. Power requirement for a stirring aerated fluids. When the stirred bioreactor is simultaneously aerated, the power requirements for stirring is decreased. So hydrodynamics in the vicinity of the gas sparger change, and the density of the fluid around the sparger and near the impeller will also change. So the equation here, okay, an approximate expression of reduced power requirement. Okay, we have the gas power Pg and P naught is the ungassed power. So you can use the equation here in order to find any variables, whether to calculate the gas power or the ungassed power. Okay, so this liquid volume is based on the working volume of the fermenter. Pg over P naught can be found with the knowledge of process parameters and impeller dimension. P naught from the equation of P naught equals to Np rho N I cube di power of 5. Thus, okay, Pg, okay, we can found from the equation, okay, previously can use this equation when you have this P naught, okay, because all the dimensions of the reactor you can calculate and you can design. Okay, so the Pg over P naught as a function of aeration, okay, then you have the Na equals to Fg over Ni di cube. The figure here shows the Pg over P naught, okay, as a function of aeration.